Yeah, I will start the talk and Andrea will close it. In fact, we wanted to share with you some examples of of the system we study at SAMBA, not all, of course, particularly those in catalysis and electrocatalysis. And I wanted to start just a very few slides, you will excuse me, about the beamline, just to present it, because it's quite used, but we don't publish much about I mean, mechanical and optical stuff. We consider it transparent, but that's an opportunity to show you what we use. So the team is me and Andrea that we are at the seminar. Gauthier is more about, he's working in environmental science. I will not speak about that. And I will always thank our mechanical engineer, Guillaume Alizon, that help us all the year long. So if I can share, well, we are installed on synchrotron SOLEIL, as you said. We are operating at 500 milliamperes in top-up mode from the beginning, and now we start to do, well, it's a long time. We started in 2006. We were younger, as you notice in the pictures, and the top-up mode ensures us a really good stability. We are on the bending magnet beamline. Since the synchrotron is not very big, we are very close to the source. This gives us the possibility to have a reasonable flux, even just collecting 1.5 milliradians horizontally times 1 vertically, with a critical energy that gives us good intensity in a region where most XF studies are performed around 15 electron volts, 18 electron volts, so 8.65 kilowatts of critical energy is very adapted. We are a very, very classical, I would say rather old setup, with a first cylindrical mirror that is collimating, a second one that is focusing vertical, and a sagittal bending monochromator. We developed, if you look in literature, the quick XFs that has been now transferred to the rock beamline. It was really demanded. At a certain point, it was impossible to work with all the activities on the same beamline. So we separated in two. We had the opportunity of having a second source. So the rock beamline was born. And now it's managed by Valérie Bruat. We had to cope for the time being with this sagittal bending monochromator that many of you know as a technique. It's very complicated to use for XFs, but finally we started from a ESRF, Oxford design, and we had to remove everything 2 years ago, and we rebuilt it from scratch in SOLEIL, and we developed a new bender without any ribs on the back, and a completely new mechanics to gain stability and remove vibration. And finally, I will not make a long story of all this, we managed to lower the beam size horizontally from 300 microns to 160 microns, and vertically we remain to the size permitted by a mirror, a cylindrical mirror. So it's rather common, 150, let's say, microns. The sides are mostly the same at all energies. And in reality, the upgrade was for removing, when you get rips on a crystal, you get spots, individual spots. Now we have a continuous beam that can be modulated in sides without having these individual spots or secondary foci. What we gain in reality was stability. So this is an example of what we can do now, and we do every day. There is no more step-by-step scans, only on-the-fly scans. So we can cover large energy domains with a sagittal bender monochromator in continuous scan. So let's say 2 minutes. It's not quick XFs. It's an XF in continuous mode. It's very effective. When we stay 20 minutes, we stay 2 minutes. That's fair for us. And they are very repeatable, as you can see from the first derivatives, very stable and low noise. This gives us the opportunity, for example, to follow processes, slow processes, but where you don't want to stop all the time or spend a day for just something that can be recorded in 2 hours. So here it's an example that I use for students, is a Prussian blue analog. So a spin transition, and we can cool it down, exposed to radiation, and make it the transition to low, high spin at low temperature. And it's very nice experiment to show to students. But in step-by-step mode, you take 3, 4, 5 XFs. In this case, you just let it working, change the temperature, and follow what happened. And it's very nice, and you can really follow the transition, even if it's not time resolved in the proper sense, it saves you time. Speed is not a matter for us, not much, because we work mostly in fluorescence. Transmission experiments are in the rock beamline. And we have a 36 pixel germanium detector from Miriam that has been several times upgraded. And we are acquiring, we will install next week, a 13 element silicon drift detector to cope with higher fluxes and with more complicated matrices. So the quick exercise is done in fluorescence. Some examples just to close this part on the beamline. This is a typical spectrum we can get in with barium when you get, sorry, there is something covering the top, but these are, I can tell you, 850 ppm, so relatively concentrated. Then we can go down to 10 ppm. This is bad spectrum, but let's measure it in 20 minutes in a complex matrix. Another example is what we can do now. In 9 hours, we can measure cadmium at 1.5 ppm. So this is the direction where we are going to, and I will explain a little bit later. Catalysts we measure are more and more complex, and they are not concentrated. Concentrated catalysts, there are many of them. They go to the rock beamline. We work mostly in cases where you can't work in transmission. So I'll leave this presentation and we go to two examples of what we do now. The main problems are facing, I think that we all present the same slides after all in the community, at the energy nexus. We start from renewable energies or non-renewable energies or nuclear energies. In any case, at a certain point, since all these sources, especially the renewable, are not continuous, in Germany they know it, they have to cope with coal to stabilize their energy grid that is not renewable at all. We need to store this energy. This excess energy has to be stored. What have been sought for years is to use hydrogen. That is very good because it's easy to produce. We know the technology, it's easy to handle, but not so easy to store, not so safe to transport. So we are seeking some alternatives. So there is an active research. My colleagues, and I will thank you them later, my colleagues chemists try to find catalysts to use these alternatives. This alternative is ammonium boride. Ammonium boride, it's solid. That's really, really handy to transport and store. From 3 moles of these, you get 3 moles, from 1 mole of these, you get 3 moles of hydrogen. How to record the hydrogen? You can use acids or you can use temperature. When you use temperature, you waste energy. When you use acids, you waste the acid that is in any case a form of energy. So the catalytic way at room temperature is the most desirable one, evolving hydrogens right by pouring the ammonia borane in water and getting back your hydrogen with a catalyst. So platinum, as always, is a good catalyst for this reaction. It is expensive, but it's a very good catalyst. So the question was, how can we tailor the catalyst? Can we improve it? And how can we reduce the size of the particles? So they started from a very practical question, and then they go for something more, first principle. The question was also to disentangle shape and size and composition inside. So what they tried to do, and we studied, was to work on bimetallic nanoparticles, palladium particles. They can mix or at the nanoscale, or they can demix and make core shells. They tried 2 different approaches. The first one was to reduce the precursors together, palladium and platinum chlorides, with mercaptoundecanoic acids protecting the particles and a reducer that common reducing sodium borhydride. In in the end, what you get is a particle, and we will see if it is what kind of particles that is covered by this protector that can functionalize it. The sulfur will go to the surface of the particle, that's for sure. I don't need access to tell it, it's just chemistry. And COH will go throughout the solution. That makes the possibility to functionalize part of the particle. Another way that we can think of is to pre-reduce platinum, that is very easy to reduce in a precise size, and use it as a seed to grow palladium on top of it with the same procedure. So we end at the end with the same protected particles. This has been developed by Matteo Carniello years ago, and I can sketch it like that. I took it from his paper that he was in the group with of my collaborators at the beginning. You start from this protected particle, then you can disperse, functionalize further with, for example, an acid-modified cerium-4 precursor, go through hydrolysis and calcination, and you get a particle that is covered with cerium oxide, for example, a second shell. And then the functionalization can be any further. And in that case, you can even functionalize alumina to bind to these particles. And through calcination at different steps, you can get particles of ceria containing the active cluster on top of alumina. So it's an ideal non-sintering catalyst. The promoter is around, ceria, is around the metallic particle, and everybody is anchored to the surface and dispersed. This is the principle. In our case, we stayed and we studied the particle, but it was then embedded in the system. So we started from platinum and palladium pure particles as a reference. And as you can see, or you can't see, I hope you can see them, they are very, very, very defined. And when we analyze Asher-10 images, you get an average particle size that is between 1.5, 1.8 nanometers. What about the co-reduced nanoparticles? It was in part a success in a certain range of concentration. If you look to the graph here, I hope you can see my pointer, from 60 to 40% of platinum or palladium. I mean, on this top it's 60% of palladium, and on the bottom you get 90% of palladium. You can analyze the average concentration with different techniques of these particles. It follows quite nicely the supposed concentration that we introduced at the beginning of the synthesis. So the metals go to the particles. And on the other side, it was a success. They succeeded. They get more or less a stable size. So we change only the composition. We don't change composition and distribution and size. That is very fine for me that I have to analyze the EXAFs. You know, when we get a broad distribution of distances, well, EXAF becomes irresponsive in some way. The same happened with the platinum palladium bimetallic particles that was produced by pre-reduction. So again, we use the platinum as a seed and we reduce the palladium on top. At the end, we have a larger, of course, concentration span, because in that case, we can just reduce palladium on top of platinum. We can use the full range of concentration. And again, the size is quite stable and is around 1.5 up to 2 nanometers. In this case, actually, it's more difficult to know by microscopy what is the size, since it's a core shell probably. So here we come in the EXAFs. This image needs some explanation. On the top, we get the palladium KH. On the right, the platinum L3H EXAFs. On the left top, we get the palladium 100%, the isolated nanoparticles, as well as on the right, the platinum pure particles. So if we concentrate on palladium particles, when we go to the core reduction, we see a difference, a striking difference with respect to, the pure particles. That means that should be some mixing, we'll see numbers. And with the pre-red, actually, the difference is there. They are not exactly the same, but that's not so much difference. Again, at 80% of palladium in the co-reduced, well, of course, they look quite similar to pure palladium, that's 80%. And the pre-red, actually, Doesn't look so different after all. It's very different when you look to the platinum edge, that's for sure. You start from a pure platinum MUA. If you look to the co-reduction, it's completely different. And the pre-reducted, you expect to find something very similar to the original particles, for sure. And again, at 80% is the same story. The co-red particles is very different from a pure one. And when you go to the pre-red, it changed, but more or less retain the structure and the imaginary part of a platinum particle. So if you look to the results of the pure palladium platinum particles, this is very important because what you notice is, of course, the presence of sulfur. There is a part of platinum palladium that is strongly bonded to sulfur. You notice that probably some of that is not on the particles and will be probably washed away in the following step of the synthesis. But the coordination numbers are not only very small, but the distances are small. That is very nice. It means this is the small size effect of the nanoparticles. This means that we are right in determining the size of the particles. They are indeed very small, probably smaller than what we deduce from microscopy. And in particularly, this is true for platinum. If we look to the bulk values, what we expect from the bulk standards, palladium should be around 2.75 and platinum 2.77. So we really have a strong effect on platinum. And what is very nice, if you could notice, that when reducing the size, the platinum-platinum distance and the palladium-palladium distance are almost the same in my error bar. So this means that we should mix in easy way and should be very compatible at these sizes, where they are less at bulk value in a large structure. And if we compare the values I found with some in literature, I took a paper from the group of Frankel of 2006. They worked in several platinum particles. In fact, the value we find at 273 is not an abnormal one. They worked in the platinum nanoparticles ranging from 0.9 to 2.4 nanometers in different environments, matrices, under helium, under hydrogen. We are right in the middle. They work at different temperatures, but when you look around the room temperature, here we are. Our platinum is very close to what they have, for example, for 0.9 nanometers particle of alumina in hydrogen. So we are suspecting expansion, but not far also from those at 2.4. So respect to this distance is not abnormal. But when we come to how can I remove this bar? Now I need to really uncreate about, yeah, wonderful, in some way. Okay, when we go to the co-reduced samples, co-reduced means those that we suspected they mix. In fact, they mix. We found distances of platinum-platinum, platinum-palladium, and vice versa. At the palladium edge, we find palladium-platinum and so on. And as we expect from the previous finding, the very similar distance at nano sites, in fact, there is no trend. We expected some fancy trend and distances during the changing the composition. They are not. There is just error bars and correlation here. In the pre-reduced distances versus composition, yeah. It's the same, actually. We don't have any trend in distances. What we have as a trend, actually, is on the pre-reduced. On the pre-reduced, what we notice is that we have a small palladium-palladium coordination number at the beginning. So we are thinking about palladium that should reduce on the surface of the platinum particles, of the pre-existing platinum particles. And when we get to 60%, actually, we have a sort of jump. And the coordination number then is stable from 60 to 100% concentration. It's intriguing, but it's not yet a result. For the other co-reduced sample, well, that's easier. You get the dilution effect. So when you decrease the concentration of palladium, the palladium-palladium coordination number decreases. That's within the error bar of this multivariate analysis. It's okay. What about the palladium-platinum coordination number that also an indication of some mixing in some way? But on the pre-reduced, actually, it decreased. So palladium-platinum coordination number decreased with a concentration of palladium. This could mean that palladium start to grow on top of other palladium atoms, probably. And co-reduce actually stay within the error bar, as we saw. That doesn't change much. Could we guess a trend? I can't. What is interesting now is to move this bar again and observe what happened here. This can be written in numbers, I prefer. It's a coordination number of platinum to platinum. When you observe the coordination number of platinum to platinum, you observe that it's always the same. That is expected since we pre-reduce nanoparticles, we always use the same batch. And they are very close to 5.3 in average. If we keep this in mind, and I can change, and we go to the last slide for this, is activity to structure relationship. If we work in basic environment, because we don't want to release sodium borhydride in acid environment. The purpose of all this is to use just a catalyst to avoid damage. At 20 degrees, and we look to the activity, actually, we can draw these curves. Time is on the x-axis, and on the y-axis, we get the, I'd like to make it disappear. Wonderful. On the y-axis, we have the number of moles of hydrogen per moles of sodium of ammonia borhydride. You look two extremes, actually. Palladium is the least active, pure palladium, and pure platinum is the most active. Well, not a big surprise, a little bit deceiving, actually, for the guys in the catalysis lab. But in the middle, actually, there is something very interesting. If you look to the numerical values in the graph, except not on the curves, and we look to the pre-reduced one, you observe a decrease in activity with a number of palladium on top. And at a certain point, at 60%, really precisely 60%, we have a drop in activity. And we join the co-reduced catalysts that were also at 60%, and then we go down to quite immediately to we stay quite constant. I mean, we go to the activity of pure palladium particle. So it was intriguing. What does it mean? If we go back to the idea of 5.4 platinum, coordination number platinum-platinum, this is exactly what you can find for a cuboctahedron with 1.5 nanometers width. It's really 3 atoms of platinum in the edge of the cuboctahedron. Now, to cover completely such a cuboctahedron, you need 63% of atoms of palladium in the composition. And that was really nice. It's the first time I encountered, that's why I show always this slide. It's the first time we really get to such a master of the making of the particles that we can have a composition structure relationship that is really revealed by EXAFs. At a certain point, you have enough atoms to cover them. This means at a certain point, there is palladium growing on palladium, but globally, at 60%, the probability of covering everything is very high, and the activity drops. The activity is not zero, you will always have holes, but at a certain point, I mean, this is a picture. So for my colleagues, it was in some way deceiving. I mean, there is no promoting effort of mixing palladium and platinum. Actually, we precisely demonstrate that it's better to have dispersed platinum than mixing it with palladium. Then we have two extremes, co-reduced, so alloys and core shell particles. It is tempting to go to water gas shift, that is mostly useful test the reaction and see if we have a metastable or not metastable system. The system is metastable, actually. When we go to oxidation step to activate the particles and remove sulfur components, and then you go to reduction steps in mild conditions, 250 degrees, we can consider them mild. Well, we converge the structures. don't make a long story of all this. If we start from the MUA or the particles we growth, we have chosen the palladium 60% as an example, co-reduced or pre-reduced, you end up, you can see it, to the same, exactly the same XF signals, co-reduced, so alloy, core shell particles, everybody goes to the same. And what it is the same is actually the core shell. When you get at the end, you get a platinum-platinum coordination that is 6.2, 5.9. We stay always in same sizes. And then the palladium, C platinum, C other palladium, and what is C? Oxygen. Platinum doesn't see any oxygen. See a little bit of palladium, you get the picture immediately. That's nice with X, you really get the picture immediately. Palladium sits outside, is in contact with the medium, with the matrix, with the atmosphere, and platinum is in the middle. So you really go immediately to core shell particles. So I just draw my conclusion on this part. The synthetic route, as you saw, really can define the bimetallic particles, and we can disentangle the different effects. Unfortunately, they are metastable. When you remove the sulfur protector, we go to core shell. So I will not use all my time. I will just quick a second example that is from small to smaller, and then leave it to Andrea and question time. We worked also on electrohydrogenation. Electrohydrogenation try to the CO2 or CO2-RR is a reaction for which we want to recycle CO2 into a valuable, again, compound to be reinjected into the economy. This is quite complicated, but CO2 is as we all know, is extremely stable from the thermodynamical point of view. You can do it in basic environment, and this actually when you produce formic acid, produce formiate. This is very expensive to separate from the solution and waste even more energy than already wasted in the process of producing formic. When you work in acid environment, you get formic acid. You can separate it very easily, but you get a high overpotential that costs energy again. And then you can produce a lot of hydrogen that you don't want in this process. But the purification is straightforward. So what I try to do, my colleagues that can tailor very much the nanostructure, is to use multi-walled carbon nanotubes that is conductor, that they are very good stable material. They functionalize that in acid environment, oxidize it, and then functionalize it with ceria, pure ceria. That cerium oxide is actually very abundant. Cerium is more abundant than copper in earth crust. So it's not a very expensive catalyst, but not a very good one all alone. It's a promoter most of the time. So they combined the two, the multi-walled carbon nanotubes and the ceria. They made it deposition on electrode, and then they made it work. As you can see, the nanoparticles of ceria are really on the carbon nanotubes. This is very nice tomography or transmission electron microscopy. And you can see the carbon and the ceria. And the distribution of sizes is again in between 1 and 5 nanometers, peaking to 2 nanometers of oxide. So what are the findings? If you look to the current against the energy, the voltage, what you can notice that the cerium nanoparticles are inactive or almost inactive. The multi-walled carbon nanotubes, not very active too, is a combination of two that is active. And when we go to the Faraday efficiency, how much current goes to hydrogen and how much current goes to formic acid, it is evident that we get a narrow voltage region where we can favor the formation of a formic acid against hydrogen evolution. That is good. That is not perfect, but of course, but it's very good. So we have a catalyst, and the question was, okay, what is doing the catalysis? What is doing ceria? And so after many measurements, the XPS measurements that are always ex situ said that there is a large amount of cerium-3. Probably many of you have been confronted to this. When you put in the XPS a ceria, you always have a lot of cerium-3. And after all, when you go to the beamline, you don't find it, or not much. The same here. When you look to these spectra, in situ spectra, I changed the potential, I'm sorry. These are against silver chloride. The previous potentials were against hydrogen electron. So these are shifted of 0.3 volts. Anyway, on full span of potentials, you don't see much. The insensitivity or non-existent cerium-3+, that's the question. And well, we worked in a real cell, we put the CO2, we put the potential, we cycled, we worked in week with Andrea. And after all, we started to concentrate on the region where the cerium-3+ should appear. This is cerium oxide, cerium-4, with characteristic to double configuration. And this is cerium-3 single configuration of lower energy. It's very characteristic, and in principle, we should be very sensitive. But well, we are sensitive if we resort to delta mu, and we integrate actually the delta mu in this region where we should expect the cerium-3 contributes most, before this region where the crystalline field actually creates a second peak. And if we do that, and we work at a potential that is a limit of the evolution of hydrogen in our cell, you can see that in argon, the cerium-3+ is very low or non-visible, nothing is changing. And when we introduce CO2, we were very happy to see that we go from 0 to something like 65% of CO2, the absolute determination I would not trust, but relatively, we produce CO2+ that, of course, remain there when we remove the potential, we go to higher potential. We never switch to oxidizing potential, doesn't make sense. You can reoxidize CO2+, but you have to go to really positive potentials. This finally means that reality, there is an effect. When we introduce CO2, the cerium+ is produced. Is it the catalytic site, or is it permitting to anchor CO2 and exchange oxygens? So CO3+ are created when CO2 is split into CO and oxygen. We don't know. In any case, there is an evident effect of CO2. So my conclusion, as certain in some way in the takeaway messages, is we need more sensitivity. Actually, we are sure that we don't have beam damage. If we go to a beamline with more photons on this system, we can produce straight oxygen. Hydrogen is produced by the beam, but we need more sensitivity. We are really at the limit of the techniques. Probably SAMBA will go to higher resolution fluorescence detection in the future for electrochemistry, actually, because this is not just a small example. There are many of them where the delta mu is at the limit of what we can do. Thank you very much. I think I talked too much.
Okay, thank you, Emiliano. Fonda. Now it's time to have questions from the audience. Any questions or comments from the audience? Okay, Professor Kiyota-Kasakura, please go ahead.
Thank you very much for your very nice talk. So can you hear me?
Yeah, we can hear you.
Okay. So I'd like to ask you the instrument. So that you said that in the first part of your talk, you said that the Zitolo monochromator is used. And I'm very much impressed that the spot size doesn't change with energy. So it means Zitolo curvature is changing with energy. Is it correct?
Is this digital dynamical focusing? So we have this painful task to coordinate at least 3 to 4 motors for a scan. So our difficulties in making it was to coordinate the motor appropriately. Sorry.
So I think that you first adjust the curvature. I mean that it is very difficult to obtain the correct coverage? So did you monitor the spot size, or first you scan the monochromator for region and you find good coverage every place and you make something database, then they operate for the user must beam time or something?
Okay, what we do at this moment, we use an approximation. It's quite good. It's by design very linear.
I see.
We change our crystal bender recently for a graded version, and now we use a sinus harm. So we are no more so linear, but we will introduce just a small correction in the code in the year to come. But it's mainly 1,000, 2,000 electromoles because it's linear. And so what we do before an experiment, we calibrate everything on two, maximum 3 points. It doesn't mean we don't need a big table. 2, 3 points. It's a work we have to do. And then we set these points that we keep for the week. In principle, you can reuse them. Then the problem sometimes is how do you calibrate? What's your reference? We have a camera with a high resolution, but if you place the camera in a different position, probably you will not get the gain of the same setup. It will be a little bit different. So repeatability of this is checked, of course, by a camera. We put the camera at the end of the beamline, at the beginning of the experiment. It's a defocus because it's the end of the beamline, and you check that the shape is the same during the week. The question you ask is reasonable. Why do we do that when we can use a mirror? It's an historical question, and actually, from one point of view, the flux, the bender can really give the maximum flux. Do we need flux or we need the stability? We need both, but stability is probably more important. And what we would like is to forget beamline and concentrate on many environments for catalysis, actually. So I think that we will go to toroidal mirror in the near future, when we will get the money for that. And on the same question is, sagittal bender means you bend the crystal. You stress it, you are not in perfect right conditions, you lose some flux, actually. With respect to the formulas and calculation, you lose some flux because you bend it. It's never perfect. So when you go to higher energy, you lose too much. You lose toroidal mirror too, but in principle less, and you have a perfectly stable movement. Like a monochromator with many motors, there is no debate.
Okay, thank you very much. Thank you very much for your wonderful technique. Okay, thank you very much.
Thanks for the discussion. Any other questions or comments? If not, we will go on to the next talk by Dr. Andrea Zitolo.
Yeah, I can share my screen.
Yeah.
I found the button.
Okay, great. Okay. Can you see my
we see
screen?
Right. Yeah.
Okay, great. So, hello everyone. Thank you again, Ito for this invitation. Well, my name is Andrea Zitolo, and my research interests are focused mainly on electrocatalysis for energy-related materials. And so this is the, sorry, I'm trying to, okay, yeah, this is the outline of my presentation. Well, there are two important processes that can help mitigate climate changes. The oxygen reduction reaction that can be used in a fuel cell system, and the CO2 reduction. And then we will discuss some future perspectives at the end of the presentation. Let's start with the first one. So what a fuel cell is? A fuel cell is an electrochemical reactor where a fuel, in the case of the proton exchange membrane fuel cell, hydrogen and an oxidant, oxygen from the air, are continuously injected into reaction zones separated by a polymeric membrane. In this device, hydrogen is oxidized at the anode and oxygen reduced at the cathode, and with the production of energy and just water. So that's a very attractive energy device. The problem is the use of platinum, because platinum and platinum-based catalysts are the most efficient materials to speed up the reactions in the systems, particularly the oxygen reduction reaction, which is the sluggish reaction. We know that platinum is expensive, even if I say that we should consider some geopolitical issues, because we have to think that platinum, most of the platinum is produced in South Africa for more than 75%. And in this country, often the production is plagued by a mine closure, strikes, and the second producer is Russia. And due to the current conflict, there will be for sure an impact on the market for this metal. So that's why we need to find alternative and a less expensive catalyst for this kind of reaction. Yeah, I'm trying to go. Sorry. Okay, yeah. So the world of low-cost catalyst for the oxygen reaction comprises different materials. We can find metal oxides. Sorry, I'm trying to. Okay, we can find metal oxides, metal nitrides, metal chalcogenides. Then there's the big family of the carbon-based materials, where we can find materials that are metal-free, and a class of materials where transition metal is important, is needed for the coordination of oxygen and the success of the reaction. So the talk will be entirely focused on this kind of materials we are studying. Okay, sorry, there's apparently a delay in the I don't know if you if you see completely the screen, or
yeah, I can see your slide.
Yeah, no, because from my point of view, yeah, I see some. Okay, great. So why the SAMBA beamline? Well, Emiliano largely discussed the characteristic of the beamline, so I can skip the slide. I would like just to underline the importance and the fact that the X-ray absorption spectroscopy is the ideal technique for study of all dispersed metal active centers, and which is also very important when we want to study these materials under realistic operando conditions. Yeah, so let's go on. Okay, well, this is a long story. It all started in 1964 when Jasinski discovered for the first time an activity of the cobalt phthalocyanine for the oxygen reduction reaction. Then all over the years, many materials, mainly based on iron and cobalt metals, were synthesized and characterized by different techniques. From a structural point of view, we can mention basically Moss-Bauer spectroscopy, but also the FT calculations, which is important. What I would like to highlight in this timeline is the fact that X-ray absorption spectroscopy has been efficiently used, I underline efficiently used, for the structural investigation of these materials quite recently, starting around 2013, and we will discuss the reason why. Here in red, these red spots are some of the milestones that we achieved thanks to the studies performed at the SAMBA beamline. The materials we are investigating are synthesized by high temperature synthesis. We mix the Z-fate, which is a MOF, the acetate of the desired metal, phenanthroline, and then after ball milling, we pyrolyze under inert atmosphere are more than 1000 degrees. Well, with this kind of pyrolysis synthesis, the problem is that metal nanoparticles are easily formed, then preventing the precise spectroscopic identification of the signals coming from the active sites. And this is an example. Here you have the Fourier transform of the X spectra of different iron-based catalysts synthesized under different conditions, where we can identify a first shell peak, which is assigned to the coordination between iron and nitrogen or oxygen, but also the iron-iron backscattering due to the formation of metal nanoparticles, except for the one of these catalysts represented by the blue curve, where we just have the first shell peak and a second shell peak, which is the assigned to the coordination with the carbon shell. So we are now able, also as different groups in the world, to control the synthesis of these materials and have something which is metal nanoparticle free, and which is the first important step for the complete and precise characterization of the active sites. Indeed, the optimization of several model structures allow to identify a porphyrinic-like arrangement of nitrogen and carbon atoms around the central metal iron center, thanks to interpretation of the XANES part of the spectrum. So we performed the theoretical XANES calculations represented by the red curves, while the experimental spectrum is represented by the black line. Moreover, in this study, we proposed two different coordination modes. Oxygen can be coordinated in a side-on mode, or we can find two oxygen molecules in end-on mode configuration along the axial direction. And this model was also supported by Mossbauer spectroscopy, where the catalyst free of metal nanoparticles, this one, while the B1 contains metal nanoparticles, this catalyst can be fitted by, this spectrum can be fitted by two doublet, D1 and D2, previously assigned to different square planar FE and 4 coordinations. For the XANES calculations, I use the MXAN procedure, where very briefly we start from an initial geometrical configuration, and we use, of course, the experimental data. Then we generate hundreds of theoretical spectra by moving the atomic coordinates and minimizing a residual function like that. Then we applied the same approach to cobalt-based catalyst. And as for iron, in the case of cobalt, the porphyrinic-like arrangements seems to be the most probable geometry to well reproduce and interpret the experimental spectrum. But unlike iron, here we can propose, there are different structures with or without oxygen, but also with the presence of defect and a lower coordination number, different structures able to reproduce the experimental data. So in the case of cobalt, we can imagine that there's a larger structural variety than in the iron-based catalyst. And this hypothesis was also nicely confirmed by an interesting STEM study showing a disordered graphitic carbon structure for another atomically dispersed cobalt-based catalyst. Second step was also to measure these materials under operando conditions. And here you can see the X-ray absorption spectra recorded in the oxygen reduction reaction window in acidic media and under oxygen. As you can see, the spectroscopic response is not the same for cobalt or iron. In the case of cobalt, there's no change by applying the potential, while for iron we can observe a nice change that can be attributed, of course, to a change in the oxidation state and in the local structure. In this representation, this is a nice study performed by the group of Qinjin Jia and Sanjeev Mukherjee. You can see how these changes are interpreted as a switch between iron 3 to iron 2, while the oxygen axial ligands is lost and an out-of-plane moiety is formed. Well, at the beginning, we also supposed an iron to low to high spin crossover manifested by this kind of change. So we decided to investigate also the spin state of these materials, and we used X-ray emission spectroscopy. So we decided to measure the XES spectra under operando conditions, measurement performed at the galaxy's beamline here at SOLEIL. Why? Because the key beta 1,3 emission offered the possibility to probe also the spin state thanks to the intensity of the satellite band. Well, switching the potential between 0.8 and 0.2 volt, there's no change. And so we concluded that there's no spin crossover for this kind of system. This is, I'd like to say that this is just a part of a larger study, also using in situ Mossbauer spectroscopy, X-ray absorption, and DFT calculations. Yeah, I'm just reading some. Okay. Well, this is the cell we use for all the operando measurements we shown and we are showing in this presentation. This is an a liquid 3-electrode liquid cell from Zanner that we adapted for X-ray absorption measurements. The cell is used in fluorescence mode. We have a platinum counter electrode, while the working electrode is a window, a graphite window where the catalyst is deposited and facing the electrolyte. And well, that's another example, because for almost 60 years, iron and cobalt-based catalysts were considered the most promising alternatives to platinum. But we recently discovered also the first P-block example of catalyst containing tin. Tin-based catalysts also exceed the state-of-art iron-based catalyst of something of 40–50% in a real fuel cell system. The synthesis is the same. This is a pyrolytic synthesis, but in this case, instead of ZIF-8, we use the polyaniline. And this is the EXAFS analysis of the tin-based catalyst. Here you have all the theoretical signals included in the calculations. The EXAFS analysis found that the vast majority of tin atoms are atomically dispersed and coordinated by 4 nitrogen atoms and 1 oxygen atoms along the axial direction. But we also find a tiny contribution, tin-tin contribution, which is consistent with the presence of nanosites tin oxide. And the coexistence of tin 2 and tin 4 species is also supported by the absorption age position of the XANES spectra. Of course, this is also supported by Mossbauer spectroscopy. identify also the presence of tin oxides and the coordination between tin and nitrogen. Okay, so with this example, I conclude the oxygen reduction reaction. And now I'd like to show you how these materials can also be used for the CO2 valorization. We know, and also Emiliano discussed, the importance of converting this molecule into valuable products. And this is just an example. I was particularly attracted by this NASA project aimed to reduce the CO2 present in the Martian atmosphere to form glucose and then use this sugar to feed microorganisms in bioreactors. So it's just to say that the carbon reduction is it's not just a matter of art. Indeed, all these materials, all these atomically dispersed materials containing manganese, iron, cobalt, nickel, copper, and zinc, so different transitional metal atoms, are all active for the CO2 reduction to CO. Well, the activity and the selectivity is not the same, because here in the so-called volcano plot, we see that iron, copper, cobalt and nickel are the most active. Then copper is not so selective because there's also a large amount of hydrogen which is produced. Anyway, we collected all the operando spectra for all these materials under CO2 reaction conditions, and a first interesting result is that all these materials are reversible. Here you can see the absorption spectra of the materials before the reaction, which is represented by the solid lines, and then after the reaction, represented by the dashed line. While here we reported the variation of the absorption age. Actually, this is the difference between the absorption age of the sample and the metal, and the absorption age of the metal foil under the applied potential. An interesting result is that manganese and cobalt don't change oxidation state during the reaction. Nickel and iron are in part reduced, while copper is completely reduced to metallic state. And this will bring us directly to the last and very interesting example, which is the CO2 reduction operated by atomically dispersed copper-based catalyst. Actually, I mean, indeed, copper under specific conditions, so at very low potential and using this electrolyte, can reduce CO2 to ethanol. Now, apart from the fact that ethanol is a valuable product, can be used as fuel, solvent, precursor for different chemicals, for other chemicals and other compounds, there are very few catalysts able to reduce CO2 to multi-carbon products with such efficiency. But which is very surprising is the operando XAS measurements, because here you had a Fourier transform during the reaction of these materials. The blue curve is the starting point, so we have the copper-nitrogen peak, characteristic of this atomically dispersed, this single atom catalyst. During the reaction, this signal disappears while the copper-copper peak appears. It means that there's the formation of metal nanoparticles, which are most likely the active species at low potential. But which is even more surprising is that after the electrolysis, this peak, copper nitrogen peak, is recovered. So the system is reversible. It means that there's a switching between between the single metal catalyst and the formation of metal nanoparticles, and this is reversible. that's very surprising and very interesting. And today, I mean, X-ray absorption spectroscopy was the only technique able to detect, able to follow this mechanism. Okay, so that's the conclusion of my presentation. We can discuss some future perspectives. Because actually, while very instructive, the behavior of these materials studied in a liquid cell working with a liquid electrolyte and a room temperature is never transferable to a real system working at high temperature, high current density, with a solid polymer electrolyte. So the goal, I mean, also the project that I'm coordinating is to realize devices that are as much close as possible to the real conditions. I let for the moment this space empty. Let's say they are working in progress. We are realizing these devices. This is just for to launch a conversation, a debate, and to highlight the importance of going in that direction if we want to really discover, study, and analyze the stability and the degradation mechanism of these materials. And this is this is my last slide. You know, we are discussing here at SOLEIL an upgrade of the machine. So we are thinking what we can do with a new source. And one idea is to have a small beam while keeping an high flux, because of course a small beam can open new opportunities for spatially resolved studies. We can study also easily solid liquid interfaces, and with a smaller beam we can of course study even smaller devices. Yeah, this is the acknowledgement part. So I thank you all of you for your attention, and all the people and the entities that made this project a reality. Thank you.
Thank you, Dr. Andrea Zitolo. Now it's open to questions and comments. Any questions and comments from the audience?
Yeah, so sorry,
Do you accept any questions and comments? Okay, Andrea, how do you get tin-based catalyst? I mean, usually, I mean, for 60 years, iron and cobalt was used. So, but tin is very far from iron, cobalt, or metal. So, how do you get how do you get the idea to get use the tin-based catalyst for that?
Yeah, that's a good question. Sorry, I just don't see the. I mean, my screen disappeared with all of you.
No, you're yeah, you
see your desktop. Don't worry, we see your desktop.
Okay, great. Well, the idea started by the group that synthesized, I mean, these materials performed some theoretical calculations about the electronic state of some metals, and tin was one of the candidates. So that's the reason. That's the reason why.
See. Okay, any other questions, comments? Okay, I just mentioned there was a discussion from Fred.
Yeah,
on the.
I have a question.
Can
I pick up just one slide because I forgot it? And Andrea, could you stop the sharing? It's very.
Yeah, I'm trying. Yeah.
You can find some sign.
Okay. Yeah.
Oh yeah.
Okay. Great. Now it's better.
Thank you very much.
Sorry.
Something Yeah, you will understand. It's something I have to do. It's the acknowledgement for my colleagues.
Oh, yeah.
I see it because the group of Paolo Fornasiero and Tiziano Montini and a good sorry, didn't put the name. Matteo Monai, that is now in Utrecht University. I have to thank them for all the good samples they supply to me. That's all. I cannot pass by that.
Okay, thanks. Okay, now, do you have any questions or comments from the audience? If not, thank you, Dr. Emiliano Fonda and Dr. Andrea Zitolo for presenting your beautiful talks.
Thank you for inviting us again.
Yeah, thank you.
Yeah, thank you again for this invitation.